Welcome to this video tutorial, which will show you how to use the FS5 SC30 integrating sphere sample cassette for quantum yield measurements. The SC30 allows you to test the quantum yield of liquid and powder samples. The liquid sample holder, as it is shown at the moment, holds the cuvette at an oblique angle to the beam path. In order to begin making a quantum yield measurement, the excitation and emission spectra of the sample you want to measure must be known. An excitation wavelength which is lower than the start of the emission spectra should be chosen. In this case, it's 450 nanometers. A cuvette containing the solvent solution is placed inside the sample cassette, and excitation and emission wavelengths are chosen to be equal, in this case 450 nanometers. The emission bandwidth is typically set to 1/10 of the excitation bandwidth. An emission scan is then set up with a start wavelength around 10 nanometers below the excitation wavelength and a stop wavelength around 10 nanometers higher than the end of the emission spectra. We choose a small step size and a large dwell time and make sure that all of the correction options are ticked. This shows you a typical spectrum obtained from the solvent emission, where you have a large scatter peak from your excitation wavelength and almost no signal for the rest of the spectra. A cuvette containing your sample is then placed in the sphere. Please note that both cuvettes should be identical and have exactly the same volume of sample and solvent. An emission scan is measured with the same settings as before, but this time you can see that the scatter peak is slightly lower and there is some emission. The two spectra are then combined on the same measurement container using the right mouse click and insert functions. You can see the difference in the scatter peak, which shows you the number of photons from the excitation light which were absorbed, and the difference in the emission spectrum range. Select Analysis and Quantum Yield to launch the Quantum Yield wizard and fill in the general settings on the Quantum Yield calculator. For liquid samples, we use only the direct measurements, but if you choose solid samples, you can also subtract the indirect illumination and signal. You can also tell the wizard whether the spectra were measured together and also whether a background subtraction algorithm is necessary, depending on whether there's a difference in the noise level where there is no light in the spectra. We then instruct the quantum yield wizard which spectra is the sample and which is the solvent, and tell the wizard the spectral ranges of the scattered peak and the emission spectra. The wizard will then calculate the quantum yield of your sample. The sphere can be used for measuring powder samples as well as liquid samples. And here you can see how you change between the cuvette sample holder for liquids and the powder sample holder for powders or solids or thin film samples. A mirror is used to reflect the illumination beam onto the powder sample position, and you can place the powder holding tray, which is the PTFE tray which can easily be washed, and also the powder blank. Powder and film samples can be placed in either the direct or indirect excitation positions. For powder and film samples, the indirect illumination contribution must be measured and accounted for. In this case, we measure 3 spectra, one of the blank, one of the sample in direct illumination position, and another of the sample in its indirect illumination position, which is shown on the right. Again, the quantum yield wizard is used. This time we select a solid sample and use indirect illumination. We instruct the quantum yield wizard as to which spectra belongs to which situation, and we tell the wizard what the scattered spectral range is and what the emission spectral range is. The last common situation is one where the excitation spectra and the emission spectra are measured in separate emission scans. This would be the case if the excitation and emission ranges are separated by a large spectral range, and this would save time by measuring them separately. Due to the dynamic range of the PMT, it is sometimes the case that we measure the scattered peak using a neutral density filter, one which has, for example, a 1% transmission. If this is the case, then we must scale the excitation peaks by a factor of 100. We combine the spectra in the same measurement container as before, and then follow the quantum yield wizard instructions. But this time we must remember to tell the quantum yield wizard that we have separate spectra for excitation and emission. This completes the FS5 video tutorial on quantum yield.